What's that? That's better. Yeah. Sometimes those cameras. Oh, yeah, all right, that's good. Sorry about that. Anyway, let's see. So let's see. So we're up here. Oh, so did that we recorded the classes are recorded and they're on, let's see, the web page. Like if you like class one. So anyway, the last class, the two's empty, but one should go to YouTube when you click it. Wait, it might be because this isn't updated. Two. Class one should go to YouTube. Yes. All right. That's good. So that's and then two should be empty. Well, two goes to something, but it isn't right. And then like one and two from the first two classes are there. I should make the ones that aren't active so no not active, but anyway, so that should be okay. Like the last class, some people tried to zoom in and then so now this is working. People are zooming in. Anyway, the Zoom link wasn't right. The Zoom link's up here someplace. There, so if you want to you can do it. I mean, I'd rather have you come in if you can, but anyway. So that and then yeah, the calendar. So let's see. I'm filling out more things. So next week Ryan's coming in, and then Lion Del Bazell tour next Friday, the 13th at 2 o'clock. Hopefully, I don't know how many are going to make it. I guess I'll ask next week and see how many are going to be there. But it looked like we could get quite a few. So it should be really good. Like all the stuff on plastics processing is there, so you can see all the things, kind of see how that stuff works. Um, so, and then they have an analytic lab too. So look at like you can basically see the entire polymer science there, like all the equipment that's used. So it's definitely worth doing. But it'll take till like at least a couple hours. So, and if you want, if there's any people that like not in the class that want to go, anybody can go. Like if you have friends or so it's out near where 275 and 71 meet, kind of like Harper's Point on Montgomery Road. So it's not far from like Costco or those places. It's like, I don't know, you might match it up with like going to Silver Spring House or something or whatever. The stuff out there. You could do it something after the tour. I mean, it's kind of like 20 minutes from here, but and then I can take two people out in my car, but I'm not coming back. So you'd be stranded out there unless you can get a ride back. So otherwise it's carpooling. I don't know if we could do something else. Probably usually carpooling works out okay. I mean, if it doesn't, we can figure something out. All right, that'll definitely be worthwhile doing. And then Snyder's from so I rescheduled the tour for that, which was supposed to be the 11th, but nobody could go. So that's now, let's see, this will go to October, right? It's October 11, I think. Yeah, at 1:30. So that's in like Vine Street, kind of like, I mean, you could almost walk there. You could walk there, but it's like two or 3 miles. So it's just kind of down the hill. Anyway, so that should be good. And then this Kelly Williams and this Katie Beers from National Institute of Standards is going to talk. I'm going to try to get her to talk about the whole federal government, not just NIST. So NIST is kind of like the NIH for science, but NIH is much larger than NIST, right? So she runs a group that does plastics recycling. Anyway, it should be interesting. I don't know her, but I know a lot of people at NIST. And the group is kind of like 6 or 7 people. They're all doing different projects. So it might be interesting to hear. But I hope she can get an overview of the government's activity, the US government kind of. So they're in Washington, D.C. So it should be interesting, I think. I hope. And then I guess that's all I have so far planned. There's a couple other people. There's nothing out in December, but basically trying to get as many people that are relevant, you know, that can come in and talk about. Oh yeah, and then yeah, Carrie from the Cincinnati um, Recycle News Center. Um, anyway, so that's kind of the logistics of things. So, and the homework, I guess one person couldn't find their homework group. Is everyone okay with that setup for homework groups? Hopefully it's all right. So again, like if there's someone that doesn't show up, let me know and I'll put them in the group 13 right now. There's one person in it. So anyway, so I don't want people that not doing anything, like you don't hear from them at all. Just send me the name that automatically go to group 13 till it fills up to probably many, 3 or 4. Then there'll be a group 14. You know, but eventually we'll have several groups. I think there will be like people that didn't show up, and then it doesn't really matter. Like, I mean, it's kind of the same work. So hopefully it'll be okay to do that. I mean, I don't think it's exactly a penalty because they get, like, once you turn your homework in, they get the grade from that homework. You can't like erase it inside Canvas. So logistically, it's not really a penalty or anything, but let's see, get rid of that. All right, so that's all okay. Everyone's all right with that. All right, so anyway, so let's see. They did put polycarbonate into this thing, so it's still a pile, but so it's slowly, I guess it's adding a few things now and then, but basically that's the pile of all the plastic in the world. Try to, I guess I can get that to do that. So last time I went through polystyrene synthesis and kind of like, oh, and then I said like the gel permeation chromatography. So I added a slide that shows it. Like when you go into a chemistry lab, we go to Lyondell, you'll see like 10 of these. Okay, so it looks like nothing, but within this box, let's see, the bottom box, I don't know why they stack. I guess it takes less space if you stack it, but each one's a component of the system. One's a pump. It's a high pressure pump. It's like 50 megapascals, so 500 atmosphere. Then it's got a tube, a metal tube with a stainless steel tube with polystyrene gel usually in it. And then you have a solvent. So when you have these, they have to always have solvent that's running through them because if this dries out, the thing doesn't work anymore. Like you have to throw it away, and this thing's 10 grand or something, that column. And then so that's always flowing solvent through it, and it's flowing through. When it runs, it's flowing through it like a milliliter a minute. And when it, so you put it in idle mode when you're not using it, and then it goes down to like, I don't know, 0.1 or something, 10 times slower, but it's always has to be wet. And then the other one is your sample jar. So there's a switch that you flick here. So like a manually operated one, there's a manual flick switch, and that starts the time. And then you get the retention time that it comes out. So it's kind of a retention volume. So it's like this speed of 2 ml per minute times the time that it's in there. Right. So you get a plot of like signal versus time, basically retention time on the bottom, which you convert to retention volume at some point. And then so basically the small, it's going through so slowly that it's thermally diffusing laterally. So the small things explore a lot of the gel kind of forest, and the large polymers kind of zip through just the main paths and come out first. So the first thing you get is big things, and later on you get smaller and smaller things. You'll get a curve like that. So if this is retention time down here, sometimes it's labeled retention volume, and then the large molecular weights here, small molecular weights there. Then you convert this into like a molecular weight distribution using like kind of a polynomial function usually. That you calibrate this with standards to the anionic polymerized polystyrene standards that are monodisperse and just have a single spike. So you get kind of a time versus a molecular weight, and then you just do a polynomial fit, and then you get to convert whatever retention time to molecular weights. Anyway, so if it's anionic polymerized, you get a fairly broad distribution. If it's anionic, you get a spike, and for a free radical, you get a broad. So the commercial materials polystyrene would normally be something like this, like a fairly broad distribution of molecular weight. And then, so you measure that by this MW over MN, which will be 1. So it's called the polydispersity index. And that would be 1 for anionic polymerized, 1.02. For this commercial free radical, it's 2.2. And for polyethylene, it can be 15. It's like high density polyethylene. If you have, so a lot of times what they'll do, they want to get polydispersity, they put in 2 different catalysts into the reactor, right? And they'll be producing 2 different molecular weights at the same time. And then also you can have this kind of backbiting mechanism where the chain more or less like doubles in molecular weight. So you can have like one peaks the main stuff you're making, and the high molecular weight one would be like a doubling of the molecular weight. So a lot of weird things can happen. You can get, it's not always a monotonic peak. It can be modal, right? And then, or it can have other features in it. If you have branching, so that's the thing. Like if you have branching, so you could have a huge molecular weight, but it's got a small volume because it's totally branched, like linear, low density polyethylene would be arboreal branch, like tree branches. And that thing would come out like early, even though it's a high molecular, it would come out late, even though it's a high molecular weight, right? So it's gonna, because it's compact, it's denser than a chain that's linear, right? So you have to figure out like how you would distinguish between a high molecular weight branch polymer and a low molecular weight linear polymer. And you do that by having different detectors on it. That's why this thing has a stack here. So if you use light scattering on this, you get the weight average molecular weight, but it's an absolute weight average molecular weight you get out of it. So that's just a straight number, and that doesn't have to do with branching or not branching. In other words, the time it spends in here, it has to do with the retention volume and the volume of the molecule. But if you shoot a beam of light through it and get the light scattering pattern, get the weight average molecular weight, then that's a tag of a molecular weight, like a fixed actual molecular weight. So by your standards, you would say that it's got 1,000 molecular weight. By your light scattering, it's coming out like 100,000. Then you know that's a branched molecule. So that's the game that these guys are playing, because they have catalyst people who are the big bucks people at Lyondell. They're at the top floor and you can't go up there. And they're mixing all kinds of foo-foo dust to see what they get out, right? But they don't know what they get out. So they're trying to make some product that's better, has higher failure strength or something for a pipe. But they don't exactly know what molecular structure they're getting out of it. So they want to know. So they're going to run it through a bunch of GPCs with a huge number of detectors. So they're going to have an index detector. That's the standard one. That's just, is there stuff there or not? Then they could have an IR detector that gives a chemical composition. They can use a light scattering detector to get the weight average molecular weight, and you can put it through a viscometer to get the viscometry molecular weight, which is a higher. So the orders go like number average, weight average, then viscosity average would be a higher order molecular weight. So they have all those in this line, and they can pretty much kind of guess what the molecular structure is by combining all those things. So there's people that are just experts in this technique to figure out the structure of polyethylene. So anyway, so this is shown for polystyrene, but then I went through anionic polymerization used to make tires like SBR rubber. Well, I didn't put in, I'm going to put in something about how you manufacture tires too, but that's a little bit of a process, but I didn't put that in yet. And then this is anionic polymerization for SBR, basically. Like you can do stepwise. You run the, this is styrene, so pH means aromatic ring, basically phenol. So you have unsaturated, and then an aromatic ring makes styrene, and then you just polymerize that with butyl lithium for anionic, and it'll just make a chain. It'll keep cooking until you run out of monomer. And then you shuffle in butadiene monomer. So it'll make it just tag on one block of styrene, one block of butadiene. So you have glassy domains. This will be glassy at room temperature, and this will be a rubber with a glass transition of -60 centigrade about. So anyway. So yeah, that's kind of what a die block. You can make a tri block, and as many blocks as you want. You can also make star polymers if you put in cross like agents that like allow branching on this thing. So anionics pretty flexible, the kind of topologies you can make. And then each of those is going to have special properties, like the star polymers are used as viscosity enhancers for oil, for synthetic oil. Like it's going to have a lot of star polymers. You just have a group that's got a bunch of, like you have like divinyl benzene would make a 4-arm star if you put it in with styrene, right? So you have, because it's got 2 vinyls, so you polymerize that into another thing, and then the other vinyl would split up. I try a 3-arm star. So you have divinyl benzene, you bond it with another divinyl benzene, you get a 6-arm star. So you just throw in these molecules that got multi-functionality, and you can make these star polymers. And they have the advantage, like in oil, that they have a flat. So usually a polymer, when you shear it, it thins out. So you have shear thinning. So the viscosity drops as you shear it. Right. So for a motor oil, that's pretty good, because you have the engine sitting there, right? And then it's got a high viscosity. So you have goo in the engine, and it's not going to leak. And then when you start running, you don't want to have a high viscosity, you want to have a low viscosity, so you don't have a lot of heat build up in the engine. So basically this kind of shear thinning behavior is pretty good. But if you can tune that behavior by throwing some stars in that have a flat viscosity, so they don't shear thin, and it's the same material, so it's miscible, then you can design engine oils that are better somehow. You know, some people just work on that kind of viscosity aspect. So they have a huge lab for viscosity. I can go through to like how you measure viscosity and things. Then I talked about ABS. So these things are polystyrene could be recycled, but it isn't, basically because of the clarity issue, I think. And then SBR can't be recycled because it's 2 things. And it's like it's not always the same composition of blocks and things. So all you can do with SBR is grind it up, which is what I'll have the Liberty Tire guys kind of come in and talk, basically over Zoom, I think, because it's in Columbus, but talk about like what they do. So 80% of waste tires are being reused now in terms of regrind. So it's quite a bit, like it's a huge fraction. It's actually probably the highest reused plastic right now, like I think, you know, and when they use it for things like I guess when they build roads, and I think it's mostly in California, but they fill underneath with rubber, you know, so they just put a whole layer of rubber instead of gravel under the highway. And that, like in earthquake areas, this turns out to be useful because it absorbs whatever's going on when it shakes. And then they use it in sports fields and things. And then, I mean, the regrind's used all over the place now. Like you can use it for rubber mulch. I have some of that. You know, some people do kind of crazy things with it, but basically it's being used, like they can separate out the steel belting and the fibers. So they have processes to do that, but it's all like really violent. Like it's huge machines like ripping the stuff apart. You know, so this Liberty Tire is the largest operation in US and Canada for doing that kind of thing. So it'll be good to hear from them when they've agreed to do it, but they haven't set up a date yet. You know, so anyway, SBR would go into that stream. That'll be like the tread compound for the rubber. I mean, so different tires use different, like natural rubber turns out has great wear resistance. It's like rubber from a rubber tree or synthetic isoprene rubber. The synthesis is the same though as butadiene. It's going to be like anionically polymerized mostly, right? So it's going to be a low temperature with this kind of nasty catalyst and then polymerization thing. So, but anyway, like truck tires use isoprene because they want to have wear more than anything else, because they have like 18 tires. You know, so they don't need to worry about one tire gripping the road, for instance, because they have 18 to grip the road. The same with airplanes. So airplanes have like 38 tires, I think, for a normal whatever jet. So it's like a huge number of tires, and they wear out. They get 14 takeoffs and landings for a tire on an airplane. And they're high performance tires. They're wear resistant in particular because when they land, it skids on the tarmac, you know. So anyway, so both the trucks and the airplanes, as they have so many tires, like if one blows out, it doesn't matter that much, right? So they basically retread the tires, and they, like an airplane tire is used over eight times It's retreaded 8 times before they throw it to the grinding machine. So actually, it's a good example of like reuse or whatever, reusing the same things. Somehow they strip the tread off the tire and strap on the tread on it. But the US, I think, is the only place in the world that retreads. Like you see the stuff on the highway that when the treads fly off, right? So that in a car, that would be like catastrophic. If you had a retread on your car and all of a sudden it blew apart, first it would rip your car, like the wheel well apart, just tear it to smithereens. And then it would fly maybe up into the passenger compartment and kill you. Or, I mean, so it's a big problem if you're riding like right next to a semi. So the truck tires are also pressurized to huge pressure. So airplane tires, I think it's like 400 pounds or something. And truck tires is something like almost like near that, Space is a huge amount of pressure. First, you have this projectile flying off the thing. And if they blow out, like they can literally blow your car off the road. So like riding right next to a semi is not, I always get pretty scared doing that. Because it's like if something happens to their tire, you're kind of out of luck. So anyway, so US, I think, is the only place, like you go to Europe and there's no tire stuff on the side of the road. Or like I know in Africa, I don't know about India, but basically, I think the US is the only place that does retreading of tires routinely for semis, but it seems to work for us somehow. But basically, you'd think someone would clean them up off the highway, for one thing. But anyway, so anyway, yeah, that's kind of like the tire thing. We'll talk about that more. I have a little section on tires, so we'll kind of go through that a little bit. But anyway, so the anionic, the stuff, I went through that. Block copolymer, ABS, not recyclable, and actually none of the styrene, butadiene, acrylonitrile circle of polymers, I think none of them are recyclable, right? So that's kind of a dead end. Like the Lego bricks are just going to go in a landfill, right? There isn't any use for those things. You could use other materials, but there's some reasons, like I showed you the video of the injection molding. There's a reason they take that. And the same, so all these kind of engineering success stories, from polymer science. So in the 60s, 70s, 80s, 90s, all these people at all these companies were working to make like a better plastic that was cheap and also could like perform way better than things like polystyrene. So all this ABS stuff is a product of like, thousands, tens of thousands of people, like scientists, like working to develop these materials. And they're like, oh yeah, we got this great stuff for Lego bricks. It's perfect for it. It released from the mold. Then like come like 2000, 2010, and then all of a sudden it's like, well, look at all this stuff piling up Lego bricks. It's like, what are we going to do about this? So it's kind of like, it's frustrating, I think, in a sense. You look at like such a success story of making new materials, then it ends up like being a problem. It's too good of a success, right? Because it lasts forever. Basically, last forever was a target for them initially, then afterwards it becomes like a problem. It's just kind of like, be careful what you wish for type issue. So anyway, this kind of hips thing, I think it was developed in the 60s to make so that plastic cups didn't crack, so your beer didn't fall over you, spray all over you when you squeeze the cup. And was a success story, but also makes it not, you can't recycle hips, because it's got butadiene in it. So there's no way you can recycle that stuff. I mean, the only way it's made is that it's like this careful mixing process that produces these domains. So you can't reproduce that in a regrind. Basically, that's a one-step thing and throw it out. So a lot of these are problems. And then the microplastic problem from the, so this was made some beautiful monodispersed spherical polystyrene beads, and also PMMA can be made this way. But basically, this is a microplastic that goes right into the environment and can't be removed once it's there. So you have kind of micron to submicron beads floating around that last forever, right? So there's problems with these things. So I went through these kinds of different polymerization schemes, injection molding, mechanical testing, crazing, and shear banding, and then I think this is where we got to. So this is like condensation polymerization. So we had like anionic polymerization, free radical polymerization. And this is like the one that a guy named Carruthers invented at DuPont in the 1950s, late 50s, I guess. The Carruthers could have won the Nobel Prize, but he made cyanide and drank it. He's one of the guys that killed himself. Right? So anyway, he probably would have won the Nobel Prize for, he invented all the condensation polymers, so PET, polycarbonate, nylon, basically everything that DuPont made, this guy invented. So Paul Flory did win the Nobel Prize. He's like the kind of one of the early US polymer science people. And he was hired at DuPont to do kind of polymer theory, and he wanted to hire someone that could do, so Flory went to Ohio State, he's like an Ohio guy, basically. And then he wanted a chemist that could make stuff that would be interesting for him to study with his kind of physics things. And he hired Carruthers to work at DuPont, and then Carruthers went on to invent all the polymers, all the major polymers, condensation type like this. So basically condensation means you're going to leave off, something's going to come off, and usually it's water or an alcohol or an acid like HCl, right? So basically you're going to have a carboxylic or a ketone group, right? And that's going to, there's a leaving group here, and you have a diol. So everything's di, right? So this is terephthalic acid. So it's got two kind of carboxylic acids on the ends. And then this is going to make methanol. The methanol is toxic. It's not a good chemical to have around. It's when you get home brew booze, it's got ethanol in it, but it's got methanol and makes you go blind. And you absorb it not through your drinking it, but through your eyes. Like the fumes of it go into your eyeball and make you blind. It's kind of a weird process, but anyway, methanol is not good to have in the lab. I'm not sure that wearing goggles will help, because it kind of gets in there. Anyway, so having an industrial process that produces methanol, in the 60s, it was great, but now it's kind of like people don't like that. So there's other things you can make in condensation. Just add another methyl group onto this and you get ethanol, right, which isn't necessarily that toxic. So anyway, so basically you combine those and it produces this, and it generates a exothermic reaction. But also so it makes an ester in the end. So you have an ester group here. So that can be de-ester. So this is a reversible reaction. If you heat it up, it'll go back to that. So it goes forward, it goes backwards, which is good for PET because you can get back to the monomer if you want by depolymerizing it through reverse esterification, I guess. But so anyway, you end up with a polyester out of this. Right, so you can see the ethylene, the terephthalic, so it's polyethylene terephthalate is what you end up with, which is a water bottle, right? So, if you look at the polymerization of that, so if you look at the free radical polymerization, you throw some radicals in, then they start growing a chain. The radical goes to the end of the chain, and it just keeps growing one chain. Right, so you immediately get high molecular weight polymer, right? So you have a one single vat process for free radical. Just like boom, you're going to get chained. With condensation, you have like a pre-polymer because you're going to get they'll pair up first, and then the pairs, so they'll just grow as like pairing sets. So you have no molecular weight all the way through the reaction until you get to 90% conversion, and all of a sudden, boom, the whole thing's one molecule, right? So it's a different kind of process. So in this kind of, if an industrial scheme for this, you're going to have take the two monomers, put them together, you have esterifications, you get dimers, or you get even just the glycolic acid, whatever, just these two combined. Then you run it through a reactor where you're going to do kind of pre-polymerization, where you get kind of a gooey slurry, and then you're going to put it to final polymerization to drive it to the end. And you drive the reaction by heating it up and pulling the water off. So usually condensation would make water. Here you're making methanol, so you'd heat it up, drive the methanol off, and it makes the reaction go forward. So the more methanol you pull off, the higher molecular weight you get. Right, so it's kind of a simple scheme. It's easy to do. I could bring it in and do that. Usually, when I taught intro to polymers, I do the nylon rope trick where you take adipic acid and diamine, and they're immiscible, so they make an interface between each other when they're in a glass. They can take tweezers and pull it, and it just polymerizes. It's like it'll eat up the two liquids to make up. It makes a plastic film between the two things, and as you pull the film out, it just generates more and more polyamide. You know, it's pretty simple to do, but the diamine is a neurogen, tetragen, carcinogen. So it's like destroys your kids and you at the same time. Like, so basically it's nasty thing that around. So I stopped doing that. Didn't affect me though. But anyway, so anyway, you have to kind of be careful about these monomers and the condensation reactions. You know? So, I mean, in this case, they aren't particularly toxic, but for like polycarbonate, one of them's phosgene, right? And for nylon, it's this amic acid stuff. So basically, some of the monomers aren't that great for you, you know. So anyway, I mean, phosgene is the Beaucage stuff like this. Okay, this is polycarbonate. So it's going to start with phosgene and then combine it with carbonate, whatever, right? So basically, and you can play around with the chemistry of this as long as it's a diol, right? You have two alcohol groups on the end. So this is used because this is kind of like a rigid. So this has some resonance structure to it. The double bonds can flip over. So it's basically a planar structure. So you have kind of like cards floating around, and then these more flexible units, like the ether. This is a completely flexible bond, the ether bond, so it can spin around. So you have like cards that spin around. That seems to be a common motif for polymers. So you have a rigid unit and a flexible unit. It ends up making a really tough polymer, right? So you can imagine that chemists have tried to engineer this as much as they can. Like Kevlar would be very similar to this. Like you'd have, except you'd have aromatic rings that are all hooked together, you know, to make a super rigid part. And then you have a kind of a spacer group in the middle. So it'd also be like a polyester like this, like PET, polycarbonate. They're all the condensation polymers, polyesters. Right? So anyway, so there's the phosgene or the Beaucage process, you might call it, you know, because this is kind of what they're making. They're trying to make polycarbonate when they killed everybody. You know, and then there's other processes that are kind of a little bit safer, where you modify this nerve gas to make something that's not as nerve gassy, right? And then, so, you know, it's kind of a wonderful polymer. It's super tough. You can't, if you try to take a CD, and I don't know if you've ever taken, I don't know if they even have CDs anymore, but you take a CD and you try to break it, like it's impossible to break. It's a thin film of polycarbonate with some aluminum on it, right? But basically not possible to break it. So they decided they would make things like windows with it, and they did. Like they made like fighter canopies with it and things. But when they put it into subway cars in New York City, so this stuff will crystallize. So it's amorphous when it's clear, but it will crystallize if it's heated up to the melting temperature, right? Like we had someplace I had the DSC thing, right? With PET. Oops, wait, somewhere here. All right, so DSC, you have an empty pan, a pan with the stuff in it. It's all thermally isolated. You heat it up to keep the temperatures in the servo, to keep the two temperatures the same. This thing with stuff in it takes more heat because there's stuff in it. So the extra heat it takes is related to the heat capacity of the material. So plot heat capacity versus the temperature. When you get to the melting point, it consumes heat to melt the thing. When it crystallizes, it gives off heat, and the glass transition looks like that, right? So all these materials be like that. So if you have a PET water bottle, so you process, the melt is over here, you're extruding it, then you have to quench it really fast to get below glass transition. Once it's here, it can't crystallize. The idea is like a game of like quenching it quickly. Same with polycarbonate. So you have to quench it quickly. So luckily the kinetics of crystallization are pretty slow because they're these bulky molecules, right? So anyway, so all the process stuff is down here, clear plastic, nice clear plastic water bottle, right? Or a CD. It has to be optically clear, right? So anyway, but if you, and same with the fighter thing, but if you somehow could bring it up, you know, all of a sudden this turns like opaque white, like a milk jug. You know, milk jug is like semi-crystalline. So the crystals are dense, the amorphous is less dense. In between, you get an index refraction difference, and it looks like milk. I mean, it looks like cloudy. Right? So that's not good if you're flying your fighter jet and like you're trying to see where you're going, right? So, and also a subway car is not good. But so the other way you can crystallize it other than thermally is just spray it with acetone and it turns out white. So in New York City, they found out that like some of the people in New York figured out that you could just take fingernail polish and throw it on the windows. So all the subway cars were suddenly all like opaque white, translucent white instead of clear. So they trashed the idea of polycarbonated windows. They didn't find out about that in jet fighters, I guess. But I mean, I guess you could, if you have CDs around, you can throw some acetone on it and watch it happen. But I think I did that in a characterization lab once. But anyway, so yeah, so this thing is another problem, like water bottles, like these big water jugs, which I'm not sure that's what this is, but the ones that are like almost human size, is that you get a byproduct when you degrade polycarbonate. You get this bisphenol A, so which is kind of related to the monomer, and that stuff is like, I think it's bad. I think it causes cancer or something. I don't remember what it does, but people are afraid of it. Right. So you don't want to have, I think they made, because it's indestructible, so a baby bottle is really good candidate to use polycarbonate, right? So you can throw it across the room and it's not going to shatter. But then they find out, well, when it depolymerizes, it makes, so it's easy to de-ester these polymers. And then when you do that, you make this phenol A, then that goes into the milk and the thing, and then the kid gets whatever, toast with this phenol A, whatever that does. So anyway, there's problems with polycarbonate, but the polycarbonate producers say that's not really a problem. Everyone else says don't use it. So then I found this thing, but it's kind of it's old. I know why it won't do it too. It's because I didn't, let's see, hold on a second. See, you have to say, okay. You have to say enable editing. Then it lets you play the video. It's like weird. Like, what does that have to do with playing a video?
Millions of data bits representing numbers, words, music, and drawings. Today, all available on compact disc. The best part for me is it's so user-friendly.
This is from like the 90s.
Compact discs are copies made from an original glass master disc. A thin plate of glass is.
I think that was the original iMac something. Anyway, it shows how you make. So they make a master for CD. It's interesting how they make it. And then they end up with this clear master, and they coat metal on it. And then they actually do injection molding on it. That's the master.
This die is.
You can click on this if you want.
A technician peels up.
Got a protective thing. That's still the master. Then this is for the injection molding. So they're going to put it into it's an injection molding machine with polycarbonate coming in, right? So anyway, so it's just this, and this just has grooves on it, right? So anyway, there's just an injection molding machine that spits these things out, and then they can produce. I think it said they make 200,000 a day in this factory. Of course, nobody uses them anymore, but basically, when they were
2,000 compact discs
it
per
was
day.
a pretty efficient process. And this is something you could not do with glass or metal, right? I mean, just you couldn't make 200,000 exactly duplicated.
And here in the pressing room, they apply the label. This step is also very fast since the machine prints.
These things are not compostable. Like you can't do anything with them. You can make them into these things you hang in the window, and the light hits them, and they kind of look pretty. People did that for a while, but that's about it. So it's a little disappointing that this technological success story ends up being ecological disaster, in a sense. So makes you wonder. Let's see. So I can get back somehow here. This guy's there. Oh, I know why. Here, I just have to go here because it's still in screen share. Like here. That didn't work. Maybe here. Yeah, that's it. All right. So anyway, that's polycarbonate. I guess you could say more about it, but do you want to say, someone wanted to hear about polycarbonate, but is there anything else you want to add to that? If you worked over at Sabic or something. But anyway, Sabic makes this stuff. That's one of the things. So anyway, with the PET, you have with PET, you're going to do what they call blow molding, which if you go to Lyondell next Friday, you'll see this. Like they have tons of blow molding, injection molding. They have the film blowing operation. They have film casting. They have everything. They have wire coating. So basically, you can see, and they're all like a real industrial scale because they try their products out there. And when they troubleshoot, so they make pellets and they sell trainloads of pellets, and they'll be like an extruder company in Indiana that's making like films for diapers. So Procter & Gamble will hire a company to make diapers, and the company that makes diapers will hire a film blowing company in Indiana. And the Indiana guys get the pellets from Lyondell. It's like multiple jobs along this line. You can work in any of those sectors of that. They're mostly people, like the meetings they go to is the SPE meeting, the Society of Plastic Engineers, which, I don't know, they have an annual meeting. It's full of guys walking around all these sectors of the industry. Not just plastics, but other things too are there. But usually, like the rubber people have their own meeting, the ACS rubber division. And then, I mean, so each of the sectors of polymers kind of has a little bit of a different club going with it. Right? So anyway, so you make this thing called a parison, which actually, it might be an old word because I haven't seen it anywhere when I look, but so parison is this little thing that looks like a test tube. There's a picture of it here. It turns out, I found out like recently that these parisins are being used. I guess they make a lot of parisins that they're going to ship to different places. So they'll make this parison in one place and they'll blow the bottle in another place. So for whatever reason, I mean, anyway, they end up with tons of these. So they use them as pill containers in the developing world. It's like so somehow these themselves have become a value item, you know, but anyway, so it's just PET. You'll extrude that part out, and then it's hot, right? And then you have a mold that's shaped like a bottle. You just blow a balloon inside the bottle, and then it cools down, makes a bottle, and it spits it out. It's a pretty nifty process, I guess. Ends up with a thing like that. Like these are incredibly thin, so there's not much like plastic in this. Most of the plastic is in this part up here. And I think another machine is injection molding polyethylene caps for it. And then there's a machine that fits the two together after they fill it with whatever water. Right? Then PET is also used for sails, for basically fabrics, and also a lot of it's used for rugs. So the regrind or the recycle stream from this can just go directly into making rugs, because rug is a really low grade material. So you spin fibers with it. Something like you have a melt, you have another extruder, runs through a plate that's got a bunch of holes in it. The holes are called dies. And there's a thing called a spinneret, and somehow that twists that into a fabric, and that gets spun into something. You can also spin it as a solution and dry it out. So you can, like nylon would be water soluble, so you can basically run a wet polymer out and then dry it off. Or Kevlar has to be run with like high acidity conditions because it's such a tough polymer. So it'll be like I think it's like an HCl solution that's being spun, and then it has to be dried, making like HCl vapors, which are really nasty. And then it's a nasty process to do that. And then if you want to gel spin high density polyethylene, you spin it in like toluene or something at high temperature, and then draw it out and make super strong fibers from it. But I'll show you a little bit about that after. But so, and then these spinning processes are going to have like a lot of times so you want to put a sizing on it. So micron on Reading Road, there's co-ops there, right? So they make sizing. They make sizing for one thing, and they get for carbon fibers for aerospace. But basically sizing, currently it's a pretty lucrative business. So each of these things has little spin-off companies. See, so you start talking about like getting rid of plastics, and then there's all these spin-off people. It's like a web of, it's complicated. So basically, you're putting a lot of people out of business. So there's this kind of opposition to it in a sense. but then there's also a motivation because they know that's the way it has to go, and everybody wants to kind of solve the problem. So everyone, like I could get someone from Michelman, and I'm pretty sure they could talk about circular economy in fibers, like how the sizing comes into play. Like if they put a different sizing on it, can make it better. Like they're trying to sell something that would fit into that scheme, right? So a lot of the business stuff is going that direction. Like there's money to be made if you could figure out better ways that would solve some problem, right? So anyway, so they're like they would be applying sizing to the fibers and different kind of coatings, and then basically spin it and then sell it, you know, for whatever they're going to use it for. Right? It could be making rugs or right. So anyway, looked at that. And then, like I said, PET can crystallize, right? And if you put solvent on it, it'll crystallize. Or if you just heat it up. So if you look, so this thing, let's see, where's the bottle here? So if you look at this, like, so this thing is blown out, and then there's a nip down at the bottom. Let's see, there's a nip at the bottom. Not sure why, but basically there's a point right here that's thicker than the rest of the bottle, right? So that point cool, and it's inside the molds, right? So it cools a lot slower than the rest of it. So that stuff actually goes through this crystallization process. So instead of going, wherever that curve is, there. So instead of going like from the melt zip down into the glass, so it locks out all the crystal, it goes like zip, and then it gets stuck here because it's too thick, so it can't cool that fast. And it goes a little bit into this part. So if you look at the bottom, underneath the water bottle, there's a nip at the bottom. I have one in here, it's got tea in it. So like right at the bottom there, it's white. So that means it crystallized. That little nip, they call it the nip. I don't know. Somehow it's involved in that thing. You get a nipping. You'll see it Lyondell if you go out there. But basically, so it can crystallize. When it crystallizes, it does this. So if you have wax, like polyethylene is kind of like really high molecular weight wax, right? So wax is 12 carbons, like dodecane. And wax forms these sheet-like crystals. That's why it's waxy, like it slides, the lubricant, right? Because the sheets of crystals like sliding against each other, and the dodecagon chains are lined up, like stacked up like little soldiers, right? So, and basically, the soldiers have a head problem because the end groups don't fit into the crystal, even in dodecane. So it has to have like a tall guy and a short guy, a tall guy and a short guy. So there's kind of jagged surface to it, right? So if you look at it, the odd ones have a bigger problem than the even ones. Like if you go up the alkanes, like decane, dodecane, let's see, dodecane's 12, it's 11, forget it. Anyway, however it goes, the melting points go like up and down, up and down, up and down, because they have this problem at the ends, and the odd ones stick out more than the even ones. So basically, there's always like this kind of interfacial problem in this kind of crystal. There's going to be aspect ratio is going to be like a sheet of paper, just like that. It ends up with this tension problem on the surface. If you make a single crystal of it, but it can only form it with kind of a tent-like, they call it a lozenge crystal that's going to be bent like that, you know, because it has this tension on the surface. It has to relieve through these kind of angle things on it. But anyway, there's a lot to the crystals. People have studied them, you know, like crazy. The thicker ones melt at higher temperature than the thin ones. The thinner the crystal, the lower the melting point. So if you have something like polyethylene that's got branching on it, well, the branches don't fit into the crystal, so that decides the thickness of the crystal if you have a regular branching and linear low density polyethylene, and that decides the melting point. And if you can get a catalyst guy to determine exactly where those little branches are along the chain, like exactly spaced, so the distance is going to determine the melting point, then you can make saran wrap. You know, basically, saran wrap is going to have small spacing between them, so it's really flexible and soft, right? And you can stretch it over and it acts the way you want. The other way to do that is to chlorinate it. So the original saran wrap was chlorinated polyethylene, but then people realized like, oh, there's HCl in my food, you know? It's like then they decided they'd go with this kind of, and when the technology developed so they could put in these little branches on it, regular spacing, so metallocene polymerization came in like the 80s, and they won a Nobel Prize for it. And then they could make saran wrap then without chlorine, right? And then that's what everyone uses now. So it's like safer, I guess. But anyway, so So anyway, that's kind of the story of the crystals. They look like these sheet-like structures. And then if you think about like 80% of the material is sheet like that, well, the only way to fit it in is to stack them like a stack of paper. So they're going to be like just like layers of paper with amorphous stuff in between them. Right, so there are 100 angstrom thick sheets, and they're going to be spaced at like maybe like 20 angstrom between the sheets of amorphous stuff, and chain ends and branches and things like that. Right, so it's going to be all the defects piled up out here, and then will be these crystal things. So if you want to have like cornflake bag, high density polyethylene, then you want to take that stuff. So you're going to go up a tube where you do a blow molding, I mean a film blowing operation. It's going to crystallize, and after it crystallizes, but then you have all these sheets, and you draw it out, and you can get them to stack up like that in the film, right? And that stops the water, moisture vapor from going through the film. So if you draw it out before it crystallizes, then you're going to get the sheets set up like this. It lets the water go through, right? Because if the chains are lined up that way, then the crystal is going to be the other way, right? So the whole processing thing is pretty intricate. Like how you make a cornflake bag isn't just so simple, you know? I mean, the original ones, probably the cornflakes were soggy. Then like they figured out, maybe by accident, how to make it right. And then some other people figured out why it happened that way, right? But anyway, so processing these kind of sheet crystals is a little bit different than any other material, right? But it also gives you the opportunity to do things, some things. So if you just crystallize it in a dish, you know, then you're going to get basically they nucleate in the middle, and then these sheets grow out, and they'll form stacks, and the stacks form fibers, and the fibers kind of twirl as they go out. So you get these what they call spherulitic crystals, but that's not seen in processing. Like in the process stuff, this is just something that happens in a lab in a microscope slide. You can make these spherulites, right? So let's see. So what are we doing? All right, so I brought some stuff, but it's not exactly ideal because I couldn't get liquid nitrogen, you know. So I wanted to show a little bit about like the glass transition behavior, which is kind of weird. Okay, so all I could get was dry ice, which is all right. So liquid nitrogen, we can get actually like a glass ball. I'll try to get liquid nitrogen next time. But anyway, you can get it to turn glassy, like so a rubber ball turns glassy. Hopefully I won't burn myself here. But so these are exactly at their glass transition. That one's glassy, right? This is a good one. All right, so we can go through the heating. So like a glass ball, so it bounces pretty good. Those are warmed up. It'll get to the glass transition temperature. It's going to act like this one, which is just pretty dead, right? But it'll eventually like hit dead. That's pretty good for the pro. So the different polymers at different glass transition temperature. All right. Wow, that's the guy. When it gets to the anyway, I have some that are at the glass transition at room temperature, like that guy. Some of these. Oh, that one's close to glass transition. So you see, like when it gets to the glass transition, like all the energy that goes into it just gets totally absorbed by the ones that are at room temperature are norbornene rather. That one's these guys are some they call it happening satellites. Anyway, like I still not see. Yeah, he'll be up more bit. I definitely have one. Maybe it's these big ones. You know? I guess that's I have this one. You can see it'll just be like lead. So this one will be bouncy when it warms up. It's cold. Anyway, so let that one up. So yeah, what I want to show is that here, let me switch to this thing. Oops. It's gonna work. So Hold on. I didn't see the want to go home. Let's see if he's working. Oh yeah, that's right. Oops, all right, so if it's like you have TG, drop the ball, it just stops. Right? That's exactly at TG. And if you're below TG, so you're less than TG, drop the ball, and it's glassy, like a glass marble, it bounces back up, right? Then when you're above TG, it does the same thing, except it's rubber elasticity that makes it do it. Right, so if you say, so what they talk about is the modulus. So there's like a storage modulus, which is what you get back. And usually it's just shear modulus, but and then there's a loss modulus, which is what you lose. So it's a heat's a given. And then this is all G double prime, it's all dead. Right? So basically, if you take the ratio of G double prime to G prime, you get this thing called tan delta. And that's going to have, basically it has a peak at the glass transition. And it's going to dip down below TG and above. And so anyway, that's it. That's kind of the scheme of what's going on. So if you're, say you're processing the material, let's see, where's the one that's frozen? All right, sitting here. Actually, it's warm away. Anyway, it'll be dead like these guys. Just like 5%. It'll be dead like that. Your transition and then glass transitional bounce like crazy with the super ball. Right? So, anyway, so that's kind of the scheme of this processing thing. So if you're trying to extrude the polymer, like you want to be up at the high end where it's not absorbing all the energy. Because if you cool it down and you're extruding it, and all that energy goes into heat, then the extruder blows up. Right? It's pretty nasty. So basically, in going below and it's a glass isn't a good thing either. Right? That's kind of a terminal state also. So basically, you have to be like far away from TG to process it because it's going to be too much energy absorbing. Right? So anyway, so yeah, so that's kind of like the picture of this thing, I guess. I wanted to kind of show you that. There's a couple things like that, and there's also like, it depends on how hard you throw it, right? So like the Play-Doh thing is a good thing for that, but takes time. But basically the Play-Doh is like liquid, you know, if you let it sit around, but it'll bounce too, like if you give it a high impact speed. So the speed of how you process it matters too. Like if you torque it up too high, you're going to be closer to the, I mean, you could get closer to the glass transition, right? You go fast and it's going to lower temperature. So basically, you're processing at a certain speed, you double the speed, well, you drop the temperature and you get your glass transition and your thing blows up. So it's kind of like a tricky material to work with in that sense, like you're processing of polymers. Let's see, so we got maybe a minute. Show what I can do in a minute. Yeah, so there's all these things about, like this would be like temperature going through. So we're kind of showing that glassy is literally like a glass marble. This leathery part is kind of like where it goes dead. And then it would be rubbery, like a rubber at a certain temperature, you know, and then and a certain speed. So the speed and the temperature couple together, they aren't independent. Then it flows if you wait for a long time, right? So it's kind of like where you go to high temperature or you wait for a long time. With the Play-Doh, the Play-Doh will like flow if you let it sit. It'll make a puddle, but if you hit it fast, then it bounces. So it's going through this transition. It's rubbery when you go fast, and it's liquid when you go slow. So it's kind of like this is time and temperature. It makes it a complicated problem. Like when the first space shuttle that blew up, so they had rubber seals in the engine. I think it was Feynman who figured it out. Like they had a group in Washington that studied this. So that it was right at 0 degrees C outside, but because the engine vibrates at a high frequency, so that means a short time. So the short time means it's actually a really low temperature. So the 0 degrees C became like -60 at that frequency compared to room temperature. So all the seals in the engine turned to glass and it basically cracked. So it blew up, right? So basically the use and the processing of polymers is always going to be kind of a complicated thing. It's more than just like looking at the modulus or something and then predicting what's going to happen, you know. So that's why they're showing all these pictures of like leathery, glassy, whatever, you know. So, and then the crystallinity adds a monkey wrench to that because you get these business about semi-crystalline behavior. So that basically that's going to add in like a composite to it, you know. So you can have this composite that can disappear when it melts. So all of a sudden, you know, the properties go to hell at some point when you melt things. And the melting point is a moving target because you can make crystals, depending on how you cooled it, make thick or thin crystals that melt at different temperatures. It's a complicated material in a sense, you know. There's a lot of things you have to kind of worry about, but anyway, so yeah, so next time I guess I'll talk about polyethylene, and then Thursday I think we have Ryan coming from Lyondell, right? So let's see, hold on, let me figure it out. September, yeah, Thursday, Ryan. So I'll talk about polyethylene Tuesday, and then Ryan will talk about polyethylene on Thursday. Just a lot of polyethylene. And then we'll do a tour around Lyondell before we make it. Okay, so, all right. All right, it's back to rubber. So, kind of. Oh, yeah. All right. Yeah, if you want. Yeah, see what they, I'm wondering what they could talk about, you know,
Yeah.
in terms of the circular economy.
Yeah, you know, there's like one thing about one talks about the circular economy.
Yes. Yeah, that would be pretty good. Yeah. Yeah, if they want to do it. Yeah. Yeah. Just they could email me or something if you wanted. Yeah. Yeah. I mean, I know them. I kind of know them. Actually, the guy Ryan is coming next week. Worked there for a while.
Yeah, it's awesome.
Yeah, he was at Lyondell, and then he started his own company doing biaxial extension, polyethylene, and then that failed, you know. And then he went to Michelman after that, and he was there I think like 5 years maybe. And then he went back to Lyondell.
Yeah. We're like in the process side, so mostly working on the chemistry aspect.
Yeah. Yeah, it's a good place. I mean, I've been out there quite a bit.
Yeah, I really like it.
Yeah. So anyway, yeah, that sounds pretty good. Yeah. All right. Yeah.